In this video, we are going to describe multi-party garbling, and more precisely, we are going to see what a multi-party garble circuit looks like. Just a remark, we are not going to describe how we generate a garble circuit, but we are only going to see its main components. We are going to describe the evaluation phase and a way to generate a garble circuit in the next videos. Okay, I would like to start by recalling how two-party garble circuit works. Note that the main difference between the two-party and the multi-party setting is that in the two-party case, we have just one party, the garbler, that generates the garble circuit. Here in the multi-party case, all the n parties involved in the computation generate the garble circuit in a distributed way. So at a very high level, YAOS protocol proceeds in this way. First of all, we have the underlying function that we want to evaluate, represented as a Boolean circuit, and this circuit is known to both parties. Then the garbler produces an encrypted version of this circuit that we call C tilde. And the garbler sends this garbler circuit to the evaluator along with an encryption of its input. Now, in order to calculate the circuit, also the evaluator needs to garble its own input. But to this end, the evaluator needs help from the garbler because only the garbler knows how to encrypt. And as you may remember, this step is done using oblivious transfer that has been introduced in a previous video, the one about YAOS garble circuit. Now, once the evaluator holds the garble circuit and the encoding of both parties' input, the evaluator can evaluate the circuit essentially without knowing anything about the circuit itself. He will obtain an encryption of the output, and then the two parties will communicate to learn the actual output. So this is a very high level idea of YAOS protocol. I want also to recall very quickly how we garble an AND gate, again in the two-party case. We are probably using a slightly different notation compared to those introduced in a previous video, but the idea is, of course, exactly the same. So we consider an AND gate with input wires U and V and output wire W. So what an AND gate does, it simply maps a pair of bits to an output bit according to the n-truth table. So for example, we will have output 1 only if both inputs are 1. Okay. And now we are going to see how we encrypt this gate. First thing we do, we replace the actual values that can be either 0 or 1 on each wire with random strings of bits, okay, in this way. And these strings of bits are typically cryptographic keys. We can imagine that these are at least 128 bits long. And these strings of bits are called labels or keys. So we replace the first two columns of the n-truth table with the keys corresponding to the wire U and V. And now what we do, we double encrypt the output key value under the keys corresponding to the input values. And we write down this value in the table. Here, just a remark, we assume that ENC is an INCCA 2K symmetric encryption scheme. Now we can delete everything from the table except the 4 ciphertexts in the last column that essentially represent an encryption of the gate. Okay. So then we permute the rows, and if at this point, if I give you this 4 type, the ciphertext, this look completely random, right? Are just a random string of bit, and from this you cannot say anything about the underlying AND gates. Okay, and this is how an AND gate is encrypted. Now, given the garble gates for each gate, we can construct, of course, the entire garble circuit. This garble circuit will consist of a garble table for every gate in the circuit, exactly as we have seen in the previous slide, keys for the input wires and keys for the output wires. So here in the picture, we have a toy example with a very simple function. And what we have 3 gates. So we have 3 garble tables, one for each gate. And then the keys for the 4 input wires. So 2 keys for each input wire. So 8 keys for the input and 2 output wires. So 4 output keys. So this is a garble circuit. And note that this is just a recap. So we are not going through the evaluation phase here. But of course, given the input keys corresponding to the input wires, it is possible to evaluate the circuit in a topological order. So here, given 2 input keys corresponding to the inputs, one for the wire U and one for the wire B, we can decrypt only one row in the corresponding table. And we can obtain an output key. And using this key, we can move on to the next gate. Okay, so this is how we can evaluate the logical order. And it's clear that in this way, the party evaluating the circuit learns absolutely nothing from this computation. Now, when we generalize this approach to the multi-party setting, we encounter 2 main issues. The first one is that we cannot let a single party encrypting the circuit. And the second one is that we need a way to compute the permutation of the rows in a garble table obliviously. Okay, so we are going to see how we solve these issues in the next slides. Okay, so as I said, the main idea is that the encryption is done by all the parties. So more concretely, in BMR, each party or a trusted dealer at the moment chooses 2 random keys for each wire in the circuit and for each party PI. So exactly as we have seen for the 2-party case, but this time this is done for each party. And at the end, instead of 2 keys for each wire, we will have 2 N keys for each wire. Okay, because each party will have 2 keys and we assume N parties. So now, given an AND gate with input wires U and V, as before, and output wire W, and given the corresponding keys, we need to encrypt the AND truth table, as we have done for the 2-party case. Now we have N output keys, 1 for each party. So we need to encrypt each of these using all the input keys from the other parties. And this is done by using a double-keyed pseudo-random function that takes 2 keys, key UA and key VB, where A and B are bits, so are in 0 and 1. So we have at the end 4 values for each party J. So 4 N ciphertext. Okay, so for each party, okay, we have the 4 rows, but since we have N parties, we have N columns. Okay, so we're 4 N ciphertext. And here in the slide, we use G for the gate index. But later in the next slide, we will use G also to denote the gate function. So keep this in mind. And this value G concatenated with J ensures that all output wire labels are masked with independent values. Okay, so now just to fix the ideas, I have expanded the previous representation of the garbled AND gate with all the 4 ciphertexts for each party. So now we know how an AND gate is garbled. Since we are assuming the existence of a trusted dealer, we are not describing the actual protocol yet. What the trusted dealer does is just samples all the random keys and generates this ciphertext. Okay. However, we are going to see how we solve the next, the second issue. So how we permute this ciphertext in a distributed way. But for doing this, we need to look a little bit deeper in the actual protocol. In order to hide which values of A and B are we dealing with, so which row we are decrypting, BMR uses the point and permute technique. So how it works, essentially for each wire U, the parties or the trusted dealer, in our case, samples a random secret bit that is called the permutation bit, and is denoted in this way, lambda U, where U is the wire. And this permutation bit is additively secret shared among the parties. So this is achieved essentially by each party choosing a random share, lambda UI, and setting the actual permutation bit as XOR of all these shares. This lambda U is used to mask the actual value on the wire and the actual on the wires, yes. And looking ahead, an evaluator will only know the masked value that here I called big lambda U. And the entire evaluation is done according to the masked values. So this masked value is also called external value. And here the actual value on the wire is denoted by alpha U. Okay, so the big lambda U is the external value, alpha U is the actual value, and lambda U is the permutation bit. So the permutation bit essentially allows to solve the problem of permuting the rows in the garbled table. So now we know how to garble an AND gate at a very high level again. And the same principle can be applied to every circuit, to every gate in the circuit. Since we assume a circuit made of just XOR and AND gates, we would like to introduce some optimization. In particular, we would like to evaluate XOR gates for free. To do this, we need to modify essentially what we have seen so far, but the change is minor, and of course the efficiency improvement is very relevant. Of course, depending on the circuit and on how many XOR gates we have. So now we are going to see how we achieve free XOR. And the free XOR technique, just a reference here, the free XOR technique for the two-party case was first introduced by Kolesnikov and Schneider in 2008. Here I'm going to describe just the multi-party case directly. And to do this, we need to slightly modify what we have seen so far. So we need to sample another string, one for each party. And this string that I denoted here with Ri, so for each party Pi, is called the global difference. And this is fixed for the entire circuit. So it's the same for every gate in the circuit. Given this Ri, for each wire in the circuit, we sample only one key instead of two. So more precisely, we sample only the key corresponding to the zero value. And the key corresponding to the value 1 is set to be the XOR of the 0 key and the global difference for each party. And this is essential enough to obtain a free XOR. However, we need to modify how we garble AND gates. So we consider again AND gates, and we use now GAB to denote the function gate with input A and B. So here GAB is AND AB, where A and B are the inputs, okay? They can be either 0, 1, so we have 4 possibilities. Okay, so this means that we can rewrite the output key in this form. So the output key is, for the output wire W, is KWCJ. And this KWCJ is equal to key W0J XORed RJ times GAB. Okay, why? Because if the output of the gate is 0, then GAB is equal to 0, and we obtain the key corresponding to the output value 0. So we obtain KW0J. That is correct. Otherwise, if the output is 1, then GAB is 1, and the output key will be key W0 plus XOR RJ. That is key W1J, as we have seen in the previous slide. Then we can rewrite the garble gates using this value for the output key KWCJ. Just remark here, GAB is a bit, okay, is the output of the AND gate with input A and B, and it's secret shared, okay. Okay, so we now try to define the gate function using the permutation bit. So we are almost done. And more precisely, we set the function gate GAB equal to this value, lambda U XOR A times lambda V XOR B XOR lambda B, where lambda U, lambda V, and lambda W are the permutation bits corresponding to the input wires U and B and the output wire W. And A and B are the input of this gate. So we have 4 values, as it should be, according to the input values. Now, if we evaluate GAB, using the external values that we have defined previously, lambda U and lambda B, we can see if we do the math, we obtain exactly the output masked value. So we obtain alpha U times beta B XOR lambda B. Okay, so we can now replace GAB with this value that we have just defined. We obtain 4 and ciphertext again. Looking at if we have the external input values, big lambda U and big lambda B, we consider the row corresponding to these values, and using the corresponding key, we can then decrypt this row. We are going to see the evaluation phase more in detail in the next video. Here we just want to justify why AND gates are garbled in this way, but maybe this will be more clear in the next video. Okay, so summing up, this is how we garble AND gates. So assuming a trusted dealer, this is pretty simple. It just samples all the randomness and generates it. And when we instantiate the trusted dealer, each party samples a global difference, so each party, say PJ, samples a global difference, RJ, a share of the permutation bit for each wire, and the 0 key, again for each wire. And then we need an MPC protocol to generate the garble gate, and we have seen in the previous slide. So given RJ and shares of a permutation bit, parties use an MPC protocol to compute this value, RJ times GAB. And then this is XORed with the sum of PRFs, and here each party can compute a PRF corresponding to their own keys, and then these are XORed together. So this step is pretty simple compared to the other one. So for each AND gates, the parties need to compute the function gate GAB. And for this, we need bit multiplication. And then we need to compute the product with the global difference for each party. And for this, we need 3n bit string multiplications. And this step is called Garbling Preprocessing. And we will see how to actually implement this procedure in the last video. So the picture summarizes the entire process. First, in the Garbling Preprocessing, we run an MPC protocol to obtain values Ri times GAB for each party I. And then we produce the actual garbled gates, and so the entire garbled circuit. And then we will have the circuit evaluation on masked values. We will see in the next video the BMR evaluation phase.